Hello, welcome to another Carbon Removal Challenge webinar. Today we are lucky to be joined by Kristian. Actually, Kristian, how do you say your last name? I always mess this up, and I want you to say your last name now.
Gubsch, just
Gubsch.
as you see it. Yeah, it
Okay.
looks a lot easier than it is a lot easier than it actually looks.
I always think that maybe there's like a different emphasis or something. Anyway, Kristian Gubsch, who is the co-founder of Mars Materials, and I don't want to steal your thunder if you're going to talk a little bit about Mars Materials and what you are, so I'll let you introduce your venture. But we're really lucky, and Kristian's going to be telling us about scalability, which is, I think, a very important thing for the people who are part of this challenge, because right now you're focusing on making your prototypes, early stage development, but there's always that question of how you take it from something small that works, but how do you make that bigger and something that can be effective on a large scale? So I'm really interested to hear what you have to say about Kristian. And for those of you who might be watching this as a recording, Kristian's presentation is interactive, so you might see myself or other members of the audience here popping in with questions or doing a call and response to some of the things that Kristian highlights as he's talking about. So, but for now, I will turn it over to Kristian. And if anyone does have a question, if you want to interject, just turn your camera on and then ask your questions as we go through this. But if you're not talking, turn your camera off. So Kristian, take it away.
All right, thanks for the introduction, Matt. I'll go ahead and share my screen with my presentation. It says it's loading right now. Can you all see it now?
Yeah, we can see it.
All right, cool. So yeah, essentially I'll be talking today a little bit about my journey as a founder, and then at a very high level, talking about what it took for us and kind of the steps we took to get to the scale we're at today. Since a lot of the ideas that are being submitted to the Carbon Removal Challenge are fairly early stage, I focus on that side of the development rather than kind of the piloting, demo, or commercial scale, but also happy to answer questions about that. But I thought for this audience, it'd be more appropriate to talk about going from idea to actually testing that idea and what comes after that. So without further ado, here's some of the purpose of the presentation. So I want to share some lessons from being an early stage climate tech founder. I started Mars with my co-founder a couple years ago. Now we met during the pandemic online, like a lot of people in this community have. And throughout that time, we bonded together because we both had a strong passion for removing CO2 from the atmosphere. And he was presenting on a panel for another group called Air Miners. And it's an online community full of people passionate about carbon dioxide removal. And he was presenting on the panel, asked for the help of a chemical engineer to help with a technology discovery that he was doing. He was looking for technologies to license from national labs. And so I was kind of in the middle of my undergrad and graduate degree, and that sounded interesting to me. So I just volunteered to help out with some of that work. And so we went through and built a technology assessment, which I can talk a little bit more about that later on. And ultimately, we selected the technology that we're commercializing today, which I'll talk a little bit more about later on in this presentation. So I want to talk about how to evaluate your technology from a high level. So how to create that assessment, what things to be thinking about, or at least the things that we thought about and that we were successful with. Explain the basics of experimental design. We found that as we're building this process, it's very important to have a very systematic design of experiments to ensure you're optimizing your time and resources, as well as to get the best information out of your process, so you can make decisions about how to scale up your process. And then just to provide an initial foundation upon which to scale your technology. So as you can see here in the image on the right, any first-time founder sees their solution as like, this is going to solve all the world's problems. And then you dig a little bit deeper and you get held back by things like physics, costs, permitting, land use, etc. The list goes on. But it's still a really fun experience to kind of get really intimate with your idea, learn the risks inside and out, and figure out how to move forward despite that. So a short poll. So if you all want in the audience, you can go to this link and submit your questions and answers, questions that you have throughout the presentation. You can also answer one of the questions. I was just curious about the different solutions that are being worked on. So you can say that there's a question about whether you're working on soil, direct air capture, mineralization. I'd just be curious what other teams are working on, and perhaps I can tailor some of my presentation to those solutions. So first, I want to start with talking about Mars Materials, my company that I co-founded back in 2020. And a little bit about me first. So I've done several different research experiences all across different parts of the climate sector. So I started with programming Raspberry Pi air quality sensors to monitor air quality in the Spokane, which is Eastern Washington University District. And we were essentially looking at how air quality affects different residents and neighborhoods in Spokane during wildfire season, because it gets really bad over there and really smoky during the summer. And so that was a really interesting project that really opened my eyes to the impacts of climate change in my local community. And it made me passionate about not only monitoring those impacts, but trying to find solutions to mitigate those impacts. So I became introduced to CO2 utilization back in 2018. I completed a research project when I was going through my undergrad in a chemical engineering lab, where I was taking CO2, capturing it in a solution, and then converting that into a compound called formic acid. And formic acid can be used on a lot of different practical applications, and also an intermediate in commercial processes. And that experience gave me hands-on laboratory experience. It gave me the opportunity to design my own experiments, but also to review the vast and quickly growing literature of CO2 utilization. Back then, the IPCC had just announced that carbon removal was absolutely necessary to hit 1.5 C. And so I think the interest and the funding and the research was really starting to ramp up around then. And as I just learned, OpenAir was also founded in 2018. So that was a pretty pivotal year for me in terms of just getting interested in terms of CO2 utilization. And then following a couple research experiences later, which I'll glaze over now, I met my co-founder, Aaron, and I talked a little bit about this experience at the beginning of the presentation, but he was looking for a chemical engineer to help with technology discovery. We created a market-focused framework that looked at 18 different technologies across various national and private labs, and ultimately, we selected nitrilation, which is the technology that we're commercializing today. So I'm going to focus on that for the rest of this presentation. So nitrilation produces a compound called acrylonitrile, and acrylonitrile is a large chemical market at $12 billion. Many different things can be made from acrylonitrile, from your keyboard keys, your carpets, the Legos, to wastewater treatment chemicals like flocculants, to carbon fibers. And essentially, we're aiming to create a future where all of these products are made from captured CO2. And the conventional process to produce acrylonitrile is called propylene oxidation. So it takes crude oil and essentially cracks that to propylene, and then propylene is passed over a catalyst in the presence of ammonia to produce acrylonitrile, which with a couple of toxic byproducts also produced, including hydrogen cyanide and acetonitrile. And our process differs from that process at scale in that we're able to take captured carbon dioxide and ethanol and convert it into a proprietary intermediate that is then converted into acrylonitrile at scale. And so this is the pathway that we're licensing from NREL, the National Renewable Energy Laboratory. And we're also backed by Breakthrough Energy Ventures. So as we scaled up, or as we began our initial technology search, we got a pre-seed, we raised a pre-seed round, we got initial funding to produce samples of our material, so we were able to prove that the technology was viable and send initial samples to customers. And we were also to secure this really large non-dilutive grant that is able to fund us throughout our scale-up efforts. So this funds, on the next slide here, you can see our commercial roadmap. This funds phase 2 of our commercial scale roadmap. So essentially, phase 1 of the project, which is not pictured here, is the production of gram samples of acrylonitrile. So we were producing these to do a tech transfer at the lab. So we went to the lab, learned the process, used the feedstock that we want to use at the pilot scale. We produced samples, we're sending those off to customers. And phase 2 is more of the optimizations work, as well as sending larger amounts of material to customers, because as you reach each phase, it's really important to maintain that customer engagement and continue showing them the progress that you're making, as well as meeting the specifications that they require. So essentially with phase 2, we're accomplishing two things. On the technical side, we're optimizing our process. So we've identified some of the shortcomings with the process at the lab scale. We've created a design of experiments targeted at reducing those shortcomings and optimizing the overall process. So increasing the yield, increasing the time on stream for the process. And on the commercial side, we're looking to give our material, our customers more of our material so that we can be fully validated as a drop-in replacement, because they want to see, does your product behave the same as the incumbent process, acrylonitrile? There's different impurities present, and they want to see, can they still make the same product profile with renewably derived acrylonitrile? And then following phase 2 is phase 3 and phase 4. So these are more commercial units. Phase 3 is a demo unit. So it's a smaller scale, fully integrated plant that can produce 5,000 to 10,000 tons a year of acrylonitrile. And then phase 4 is the commercial plant, which is at least 50,000 tons a year of material. So just in case you know anyone that is looking for an opportunity in the climate space, we're hiring for various positions, and you can find more information on our website. So that's exciting. And we also have a website, marsmaterials.tech, if you want to learn more about our process or are interested in sharing some of our job postings. So I think that's a little bit about the company, just kind of a high level overview. And now I want to dive into the specifics of the scale up and talk about our journey. I wanted to give this overview first so that I can reference kind of our process at various stages in subsequent slides. So I can stop there for now. Does anyone have any questions? Greg, thank you for your question.
I was going to say I was going to point to the question in the chat, but you got it. Okay, I'll turn myself off.
Yeah, so
actually, do you mind repeating the question before you answer it, Kristian?
Yeah, so the question is, so this is the back end of a DAC or CCS process, and that's correct. Our process is downstream of the direct air capture or CCS process. So essentially, we have the technology to convert the CO2 derived intermediate into acrylonitrile, and then the actual capture of the CO2 happens upstream of our process.
Yeah, thank you. I would also follow up with that question. So how could this possibly be economically viable if you're competing with conventional sources of this organic molecule, and you've got this huge cost up front of either doing DAC or obviously it's cheaper to do CCS?
Yeah, that's a great question. So our process is able to also take carbon monoxide in as a feedstock. So we're looking at opportunities. I mean, our scale up roadmap, as you can see here, we won't launch our first of a kind commercial plant until 2029. So we're looking for these CCS and DAC processes to drop in cost as we scale, but at the same time, we understand that the cost could still remain high. So we're looking to source or potentially co-locate with ethanol or steel mills. Steel mills produce pure streams of CO as an off gas, so that would be an opportunity to utilize that directly, or in the interim utilize green sources of ethanol or CO.
Great, thank you.
Yeah. So yeah, that's a little bit about our process, and the economics are a huge part in terms of the scale up, and I can talk a little bit about how we assess those without having to do a rigorous techno-economic assessment, which I know Grant has presented already before when we've had his templates to be extremely helpful. So essentially, how do you get from an idea to launch? So I know that a lot of the companies that are, or I guess the entities that are participating in this carbon removal challenge have an idea. And so what does it look like to go from having that initial idea to actually launching the product? And so today I just wanted to talk a little bit about how you get from that initial idea to assessing that idea and doing some initial fact finding and discovery. And then how do you test that idea? How do you experiment? And what was the best way to approach that? So that's what we'll cover today. And if we have time, we'll also can answer any other questions that people have. So yeah, in terms of assessing technology, we want to essentially compare the technology to similar tech on a cost, technology readiness level, and impact basis. So the technology, essentially how you get there is you have to think about the market. So what are the number of markets that are available for your product? For acrylonitrile, that looks like you can sell into carbon fiber, there's plastics, there's rubbers, there's wastewater treatment chemicals. For your technology, how many different markets are there? What market is, what are the market sizes? So how much demand is there in each market? For example, if you're selling CO2, there could be a variety of different off-takers that are using the CO2 for different use cases, and potentially there's a price differential there. And what you're looking for in terms of a market size, if you're looking to raise dilutive funding, which is from venture capital, is a market of at least $1 billion, and you want to have several potential buyers in the industry. So in our industry, we have many different customers, and they all have very many different requirements. And so you want to think about, with each potential buyer, what are the specs? Maybe one buyer requires a certain purity of CO2 or a certain level of, let's say, permanence for if they're buying an offset from you. And what do your competitors look like? Who are the other existing players in the market? What's the history of that market? And really understanding and diving deep into some of those questions can help you get a better sense of where you stack up and how you can position yourself for success. The second thing that we considered was around technology. So technology readiness level is a common scale from 1 to 9 that's used to measure what maturity your technology is at. So TRL1 being just at the very early lab stage, like barely past just scratching out an idea, and TRL9 being commercial ready. So our technology today is at TRL3. So we have a bench scale unit that's able to produce material. And by the time we're finished piloting, it will be at TRL6. So we'll have that pilot unit getting ready to go to our first small scale commercial plant. You need to think about raw material availability. So if let's take direct air capture as another example. If you have a direct air capture technology, where are you getting your solvent from or your sorbent? Where is the material to make your modules coming from? How are you going to access all of that? And for some, especially in the chemicals industry, raw material availability is a huge thing, especially with the supply chain shocks that we're seeing throughout COVID. It was really difficult to secure certain raw materials, and there was a lack of demand for things like, crude oil in particular, was just very volatile throughout that period. And so how are you going to deal with if you can't have access to one of your key raw materials, how are you going to create redundancy to ensure that you can have access to that when things get difficult? So that's something not necessarily to think about super early on in the process, but it is something to ponder. And then the cost per ton of carbon dioxide is another thing that's really important to consider. So that goes in with your probably the techno-economic assessment, but if you're just doing from a high level, you can think about, all right, what are other people, if you look at your competitors, what are they saying their cost per ton on a CO2 basis, and what assumptions would you have to make with your technology in order to be more advantageous to that? In addition to that, you can think about what is the CapEx that you're going to have. Are a lot of your pieces of equipment going to be custom made? Because if so, that could drive up the cost of CapEx versus just being an off-the-shelf part. For us, we utilize a fixed bed reactor. That's just essentially a steel tube with a bunch of catalyst in it. Fairly inexpensive, fairly common piece of equipment that you can get. What's the operating expenses? So are your raw materials really expensive? Are they really rare? Are you using a lot of rare metals in your process? Generally, if your technology has one piece about it that's like custom or specific to it, you don't necessarily want to keep stacking on all of those specificities in your technology, because that will increase, essentially compound the risk of your scale up. If you use very rare metals on a custom system, that's going to drive up the cost of everything with the process. So I'd recommend making sure that where you can, start simple and then work in complexity. It makes the scale up process a lot easier, even though it is really fun to over engineer things at the beginning. And then finally, Impact. So a lot of funders will be looking at how much CO2 are you going to remove by 2050? What's the energy usage? What's the land footprint? How much space does your technology occupy? What other environmental impacts do you have? Do you use a expensive or potentially toxic solvent in your process or chemical? What are what are you going to use to manage that process or that chemical, and how are you going to deal with it? So essentially, like from a high level, this is how we looked at all of the technologies that we assessed. We looked at the market, we looked at the technology, and then we looked at the potential impact. And from just a high level assessment, we kind of put a lot of these questions into a spreadsheet, and we were able to compare technologies across the board relatively easily. And it gave us a very high level look on how everything stacked up against each other. And some other tips for gathering preliminary data is getting some of that comparative analysis. So looking at the competitors, looking at other people in the space and figuring out how they stack up to your process. And also looking at the incumbents, seeing what people before you have created can be very valuable. So in our process, we know that the acrylonitrile, the Ohio process, the incumbent acrylonitrile process has been around since the 60s. What are their costs of raw materials? What are their CapEx? What's their OpEx? And we can use that as a benchmark for what we need to beat in terms of our technology. You also need to conduct a literature review. And so that's just going through, I'm sure many of you have done this for your own technologies, but in case you aren't familiar, just looking at similar pieces of literature from your technology. So for us, that would be looking at different other ways to produce acrylonitrile. What has been researched? Why is our technology particularly advantaged compared to others, et cetera. And then just doing discovery. So talking to people, making assumptions when data is unavailable, and then checking those assumptions and making sure that they don't become fact as you go through the process of scaling up. That's probably the biggest danger whenever you're scaling up, is if you make an assumption and that assumption lingers throughout your process and throughout your plans, that can cause huge issues down the line. And I've seen a lot of engineering teams and other climate tech companies make this mistake from the early stage, and it's really important to keep track of those as you're scaling up. So another thing to do is to seek funding opportunities once you have that initial technology assessment completed. So I got this funny kind of spammy email from someone after we got funded, and they you'll get to look forward to those once you're fully funded. But essentially there's tons of opportunities out there for climate tech companies. There's accelerators, there's grants, there's dilutive capital, and I'll go into some of the resources that are out there. But essentially, all of these funds are available to help you get your idea off the ground. And there's a lot of kind of low risk opportunities where you can just test your idea. You can get introductions to potential customers. You can get introductions to other supporters in the space. Maybe that's an engineering procurement contractor, and they're willing to manufacture your equipment or run your process for you because you don't have a lab space yet. As just one example, they can get you these introductions to key players. And as an example, we participated in 2 climate accelerators back in 2020. In the summer, 2021, we participated in Venture for Climate Tech and Carbon to Value. And throughout both of those programs, we were able to get introductions to key advisors for our technology that we still utilize today. So these advisors provide guidance on our scale up roadmap, and we're able to utilize them whenever we have questions about our process. If we are wondering which analytical test to use in order to characterize our sample, we can run our procedure by our advisors first before executing it. And that can be an invaluable way to limit mistakes and move forward efficiently. So yeah, that's a little bit about some of the opportunities, even that a high level assessment that I talked about earlier can provide. If you have done some of that initial work without any funding available, you can begin to take advantage of the myriad of funding opportunities that are out there. So after that comes the fun part of experimentation. So essentially that is where we're entering with our pilot unit. You get to optimize your limited resources to extract useful information from your process. So essentially you start with a problem statement. So you say, oh, my product yield is very low. Why is that? And you list some of the experimental objectives. So I want to test X, Y, and Z to see if we can increase the product yield. You list some of the dependent variables. So in the case of a direct air capture system, that could be the grams of CO2 captured per grams of solvent. In the case of our system, this would be things like the product yield, the selectivity, and the deactivation rate of the catalyst. And you can list some of the experimental inputs needed to change that. So in our process, that's things like the ratios of the feedstocks to each other. So how much ammonia are we feeding into the system, and how does that affect the catalyst deactivation? What's our temperature? What's the pressure? What's the contact time on the catalyst? What's the weight hourly space velocity? So what's the mass of feedstock that's flowing per mass of catalyst per hour, and stuff like that. And from these dependent variables, I would think very carefully about values that can be independent as they're scaled up. And what I mean by that is think about the data you're collecting and think about how relevant it will be at the pilot scale or the demo scale, the commercial scale. One of those parameters for at least reaction chemistry is weight hourly space velocity. If you have a certain ratio of your grams of feedstock per gram of catalyst, you can use that ratio to, and it's the same for whether you're at the lab scale compared to the pilot compared to the commercial scale. And so find some of these scale agnostic parameters that you can measure, because that will help you throughout your scale up process, and just give you better information to start with when you get to each of those stages. And another thing that I think is can be overlooked is all the variables that need to be controlled. I just listed this out for our process, and there's a surprising amount of things that need to be controlled for the process to work. So let's say you have 3 different direct air capture modules, and you think they're the same, but perhaps there's a little bit more sorbent on one than the other, and that causes the total amount of CO2 captured to be less. That's just an off-the-cuff example. But essentially for like our pilot unit, we have 3 identical units. We want to make sure that they're made of the same materials. They have similar heat transfer rates. They have everything as much as you can. You want that to be the same so that you can compare the data and you can be confident that the data collected on one module or unit can be compared to the others. And that goes for other runs as well. And a lot of this may be pretty obvious, but I found that a lot of this stuff can be overlooked and taken for granted if not done systematically in kind of the step-by-step way. And then the final thing in this kind of list is to generate a design of experiments. So that's your experimental matrix where you get to see your entire operating space. You get to see kind of what are the max flow rates, temperatures, pressures that I'm testing at, what are the minimum, what's kind of the in-between, what are the ranges of my process. And based on the results from that, you can get a really good picture of your overall process optimization and operating space. So some quick design of experiments tips. So it can be really tempting to just kind of arbitrarily test different parameters in your process. And so you want to make sure that you're spending money and time on measurement devices, because the delays can be really costly compared to the upfront investment that it takes to get those measurement devices. So for example, our process, in order to analyze purity, you need gas chromatography. So we could alternatively ship out our samples to a third-party lab, and then there will be a delay, and we won't know exactly what the results of our experiment are until a week or 2 weeks later, say. That's a huge disadvantage, because you could be iterating towards a specific point in that week or 2 weeks that it takes for you to get your results back. So having timely response and feedback for your process is huge, and being able to scale up. And I think from talking with other climate tech companies, a lot of them have told me, a lot of the engineers and chief technology officers have told me that they wish they would have spent more time on analytical. It's kind of the non-sexy, boring part of experimentation, but you really, really want to make sure that you have those accurate measurements that you can use to keep moving forward. You want to make sure you take diligent lab notes, of course. I feel like that's another kind of obvious one, but you would be surprised at going back, looking at other lab notes and seeing it's just important to make sure that the lab notes that you take are diligent. Perhaps there's a system in which your company takes certain lab notes and documents certain IP. You want to make sure that all of the lab notes are kept internal and that they're documented very well so that they could be the foundation for potential patents in the future, which will drive up the value of your company and protect your place in your market. And then you also want to start with what you're trying to learn, then work backwards. So for us, we're trying to learn how do we get to 1,000 continuous operating hours? And then we work backwards. Well, we need to make sure that our catalyst doesn't deactivate really quickly. Well, what affects catalyst deactivation? You keep asking these questions until you get to the core of what you're trying to test. So that would be for us, the contact time, the weight hourly space velocity, et cetera. And then you can utilize a software like Minitab or Python to generate the design of experiments matrix. And then you can kind of systematically work through that. And what that looks like is you have your specific parameters that you're running for your experiment, and then you just kind of work down that list in a systematic way in order to produce some meaningful results. And there's a lot to generating a design of experiments matrix, and so I'm not going to get into that today, because I think that gets a little bit in the weeds, but happy to answer any questions specifically about the different types of matrices out there. And then finally, just to end the presentation and leave some time for questions, I have some helpful resources for getting off the ground that we found to be super helpful, and especially for those early stage kind of idea level startups. For one, there's the lab embedded entrepreneurship programs, or LEAP programs, that are offered by the national labs. So some examples of those programs are Chain Reaction Innovations, Westgate, Cyclotron Roads. And essentially these programs give you the opportunity to receive grant money, but also work with national lab researchers to develop your technology. So you won't necessarily have to have the expertise to do these experiments or run an instrument. They have all of that on site. They have staff that they can dedicate to helping your team. And it can be a huge accelerant in terms of getting your technology to where it needs to be. Again, there's a couple other companies out there, or accelerators out there, that I mentioned previously: Venture for Climate Tech, Carbon to Value, as well as the Air Miners Launchpad for ideas. And just getting those developed. I think especially in the US and EU, there's a lot more resources than there was when even we started. And so this is just a very short list for the almost endless resources that I'm sure are out there. And happy to, as I said, talk a little bit more about other programs that might exist. And then some additional resources that I found really helpful when initially thinking about how to assess our technology and move forward. The Global CO2 Initiative, of course, is one of the most rigorous assessments I've found. And perhaps you don't have enough information at this stage, or it might be a little too rigorous for the assessment that you're looking to do. Perhaps you're looking to do more of a high level one like we did for our process. But once you start getting into needing to conduct a techno-economic assessment and life cycle assessment, which are often required to raise a pre-seed or seed funding round, you'll want to take a look at some of the templates created by Grant, who's also one of the volunteers for this challenge. And then the National Institute of Standards and Technology's Design of Experiments guidance I found to be extremely helpful. They set the standards across the board for measurements in some scientific and research settings. And their Design of Experiments guidance has been super helpful in guiding my own thinking as we've worked to scale up our process systematically. So yeah, that's a little bit about our company and our process, and I'm happy to answer any questions.
Thanks so much, Kristian. First of all, I just want to point out to your shout out there that the Global CO2 Initiative is a partner of the Carbon Removal Challenge. And obviously, in addition to the great work that Grant's been putting in on helping us make this a reality. So yeah, definitely a great resource to have all around for this stuff. I want to actually start the questions with I think it's sort of a basic question that sort of goes to what some of our teams are looking at right now, which is, when is it the right time to start thinking about scalability for your technology? Is it something that you should be thinking about before you even start to build something? Is it something that you should consider after you've got something working? Is it something that you wait to see some responses for? When do you think obviously like the earlier the better in some ways, but I could see it being limiting if you're thinking about scalability before you even have started to build something or got something functional. So in your opinion, when's the right time to sort of start considering that?
Yeah, that's an excellent question. And I think we had a little bit of a head start in this area because the NREL technology that we selected to commercialize and a life cycle assessment had already been completed, a techno-economic assessment had already been completed. And so we got to start kind of a lot farther along than a lot of these teams. And so I would say like initially at the beginning, perhaps scalability isn't it doesn't need to be the greatest focus. Like make sure that your technology is like, I would say ensure that there's somewhat of a market there. Like I said earlier, the benchmark was about $1 billion. And if you're selling like CO2 offsets or whatever, look into specifically kind of what that market is. But the other things I would say on the scalability front is make sure that, I think with these technologies, it's easy to get carried away with building this really like sexy system that can take CO2 out of the atmosphere and convert it into something valuable and kind of do all of these things all at once. I would say choose something very particular and specific about your technology, focus in on that and keep those other ideas that you have for your technology around, because it's easy to get very distracted and kind of very broad, and that can waste a lot of time and resources as you work to scale up. So focus on that one thing. Test that as much as you can. Do some like back of the envelope calculations in terms of the impact, how much CO2 could it potentially capture. Maybe do some small scale tests if possible. If that's not possible, then write proposals and apply for these accelerator programs, because they'll be more than happy to fund kind of a well thought out technology idea. And I would say once you get past the initial kind of does this work or can this work, then you should start thinking about, all right, what does this look like at scale? I think the first question you need to ask is, can this work in general? And the second question is, can this work at scale? Like, yes, I can demonstrate that it can capture CO2 on my desk, but does it work? Do the economics work? Is there a market? Can I source all of the materials for this in a timely manner? It gets really complicated really quickly, and I think that can be pretty overwhelming. And so I would just say, yeah, focus on demonstration and viability at first, and then slowly introduce more and more complexity to the process. If you try to tackle it all at once, I think it's just too overwhelming and too time consuming to tackle initially.
Yeah, I think that's a good advice, and I think probably something that the challengers should keep in mind. I want to also ask you, we were talking about the design of experiments. One of the things that struck me was you were talking about keep asking questions until you get to the core. Do you have like a methodology for making sure that you're asking the right questions? How do you develop those questions? And like, how do you know that you're actually asking the right questions?
Yeah, that's a great question. The
methodology on it was perfect. So
I would say in terms of like whether we know we're asking the right questions or not, we rely pretty heavily on our advisors that have a lot of scale up experience. So they can provide, like, one of the things that I found most insightful about our scale up process is just thinking about collection of data in a way that's agnostic to scale. So I was talking about the weight hourly space velocity for a catalytic bed, and that's essentially like the grams per hour of your feed that you're feeding in against your grams of catalyst, and that scales up with, like, you can use that ratio at a larger scale versus at the bench scale. And so if you can find those parameters that are potentially scale agnostic, so things, I don't know off the top of my head what an example would be for like a direct air capture, another carbon removal solution. But if you can find scale agnostic data points to collect, then you can use that to inform your pilot scale, demo scale. You can use those same ratios or numbers as assumptions for later on. So I'd say that's around like some of the right questions that we were asking, like what are those scale agnostic parameters that we can measure here that also apply at larger scales? So maybe that's your, I don't know, CO2 saturation rate or something. Like perhaps the amount of CO2 you can capture per gram of sorbent is the exact same, whether it's at bench scale or the large scale. I don't know. So yeah, I would say that. And then in terms of other questions that you should be asking, I think relying on expertise is really helpful there. So asking your advisors, what should I be thinking about? And through some of these accelerators, we've gained some really outstanding advisors. We have our VP of engineering has over 40 years of experience, has built over 70 demonstration and pilot plants across the world. And so you want to find these really experienced kind of almost retiree people who are just like really excited to give back their knowledge to these young and energetic teams. And so I would say humility is huge in these aspects. Don't think you know everything about your process. It can be easy to fall into that trap because it's your baby and you perhaps invented it and you think no one else can give me guidance on how this could work. But I think having humility and just being ready to ask a lot of dumb questions and feel I guess, quote unquote, dumb about some of this stuff is totally normal and is all part of the scale up process. There'll be tons of challenges as you scale up, and it's better to ask tons of quote unquote dumb questions than get surprises when you start to turn on your pilot plan or your demo plan or whatever you're building.
So I think this is probably going to be the final question, unless we get another one in from the audience while I'm asking it or while you're answering it. This is more of a personal question, I guess.
Okay.
So you initially you were joining. I believe you were just about to enter grad school when you joined OpenAir, and obviously since then you've finished grad school, you're doing Mars Materials now. Most of our challenge students are undergrads. We have some grad students. Just kind of what was your mindset when you were in undergrad? Did you think did you know you were going to go to grad school? Do you recommend going to grad school? Did you think that you'd be doing something like you're doing now? Like, when did you start to envision that you'd be doing something like Mars? Where in your sort of academic process did that sort of come about? And do you have any sort of advice about going to grad school, when to do a startup? What sort of if one of our participants wanted to follow in your footsteps, how would you sort of frame it for them?
Yeah, that's a good question, and something I thought a lot about. Like when I looked at other entrepreneurs and I was in undergrad, I was like, how do I get to that position? And I found that just talking to other people in the field like yourself, and I connected. I mean, that's how I found OpenAir, was just reaching out to random people on LinkedIn. And then I think I connected with Ari, and then he was like, oh yeah, I just founded this OpenAir group. You should join the Discord. And I joined. And I think talking to people was huge for me. And in terms of going to grad school, honestly, I'm not sure I would have still gone to grad school had I known that I was going to start this company while being over there, because I was doing Mars stuff in the evening, going to grad school during the day. And that was, it was a lot, but it was also the pandemic. So I had the bandwidth to do that. There wasn't much else to do, but it was really exciting because I didn't see this. I wasn't necessarily looking for this opportunity. I wasn't trying to start a company. I just stumbled into this because I was networking and talking to people and willing to help out. I was willing to lend my time and some of my, expertise in chemical engineering to someone who didn't have that background, but was an excellent business person and a former entrepreneur and ready to make things happen. So that combination of kind of this nerdy learner research guy with this like action oriented, like let's kind of put this at scale, was like the perfect combination. And I would say, if you're a student, don't necessarily like try to force something if it doesn't feel right. Like, have those conversations, but I would say the best way to find a co-founder is just through organic interaction. I know that can be very challenging sometimes because you want to just go and you want to find the person and just hope that they work out. But it's kind of a big deal to be starting a company with someone. It's almost like a marriage in a lot of ways. You go through a lot of trials and tribulations, and you have your ups and your downs, and it can be a very difficult process. So I would say, if you are a student, don't rush into becoming an entrepreneur. You have your, entire career ahead of you to also start another company. But at the same time, in the same breath, I would also say, now is the time to start a climate company. Like, there's so much funding out there. There's a lot of, this is the opportunity in your career to take a lot of risks. You haven't built this long and distinguished career, so you aren't risking a lot of your career path in order to pursue something. I think a lot of people will find starting a company like very admirable, and you'll learn a lot of skills that you wouldn't have otherwise used that can be valuable in future job opportunities. So I don't think there's a lot of necessarily downside risk for a student starting a company. that's just my take on it. But at the same time, it's important to still take it seriously and not rush into building your team and your company and getting to scale as fast as you can. At Mars, we like to be really diligent, take things slowly, and yeah, it doesn't go as quickly as we might expect. But in the long run, it does save us a lot of time and money because we aren't making decisions based on impulses. We have a process for making decisions. We have a process for allocating resources, and all of that prevents us from making huge mistakes that cost us a lot of time and money. So yeah, that's what I would say for the students.
Thank you so much, Kristian. Yeah, I can definitely relate to the part about having co-founders sort of being like in a marriage with ups and downs, but more ups and downs if you're in a good marriage or a good co-founding situation. And yeah, I think that, the one of the points that was really well made there is, the openness to just talk to people, ask questions, meet new people, find people to talk to about things. It's a big part of the reason why we're doing this challenge. And we're trying to have people who are, established in the climate industry, but also early career for these students to connect with and sort of be role models for them to get into this industry. I think is hopefully going to be really helpful for them to be able to make the break into the carbon removal industry. So thank you so much for your time and this presentation. Grant, do you have a question? Do you want to?
Yeah, I have three hopefully quick questions.
3 questions.
Well, they're short. They're short.
All right. I'll turn off my camera. You go.
Okay, thanks. Yeah, thanks for the talk, Kristian. Okay, just 3 questions. One, I was curious, like, where does the nitrogen in your acrylonitrile come from? Because so it was just the ethanol and the captured CO2. So that's one. 2, I'm curious about the how you're thinking about the duration of CO2 storage in the final products that you're making, and how that might vary between different end products. And then 3 was, do you have any competitors?
Yeah, excellent questions. So the first one, I didn't have it on the slide because it wasn't our full process slide, but we utilize ammonia in our process. And I realize that's a very carbon intensive feedstock. So we're looking at other nitrogen sources as well as alternative routes. We've identified some alternative routes to ammonia that we're exploring more as we go to our commercial plant. But that's where the nitrogen and the acrylonitrile comes from. For the second question around, was that the permanence question?
Yeah.
Is that third? Okay, yeah, the permanence question. So for better or for worse, we're based in California, and they don't necessarily like the plastics aspect of our process. But for permanence, that's a really good thing because our downstream products don't degrade over time. So for example, if we're producing polyacrylonitrile and that's converted to carbon fiber is an extremely durable material and it does not degrade in the natural environment. So the carbon that's injected into our ACN and is stored in carbon fiber is stored for the long term. And that's actually why we're chartered as a public benefit corporation, is to store captured carbon into long-lived products. So that's essentially our mission statement, and we're looking to achieve that. But we understand that the long-livedness of our products is also a problem if it ends up in the natural environment. So we're looking at ways that we can recycle the carbon fiber. So there's a few companies out there that can repurpose carbon fiber at the end of life and turn it into 3D printing filaments or other use cases as well. So the end of life for our materials is also really important for us to think about and manage as we scale up. And then the third one, what was the third question again?
Do you have any competitors other than just the status quo?
Yeah, there's several other competitors in the industry. So there's one that does municipal solid waste, and they convert that to acrylonitrile. And my understanding is that process is much more expensive, but I've heard that some companies use that to they just buy that to say that they're using a green alternative. So that's one option. There's another option that uses glycerol, and it's an oxidation process. And then there's us. So there's essentially 3 other alternatives out there. And I think there's one other one that I just came across today that utilizes biomass and converts that to propylene, and then converts that to acrylonitrile via the propylene oxidation process. So essentially, there's the municipal solid waste and biomass to propylene, and then the conventional oxidation. There's glycerol oxidation, and then there's nitrilation. So yeah, those are the 3 processes that I'm aware of to date.
Okay, interesting. Yeah, thanks for sharing that. I was also just wondering if there were, like, if there's any risk from, say, conventional refineries trying to lower their carbon footprint and then selling like low carbon propylene, and then maybe also getting some kind of green ammonia. Um, and if that's like could be a source of competition, but I'm not sure if that's even
Yeah,
in
I would
pipeline.
say the main cost advantage for our process at least is the stability of the price. As you know, crude oil can fluctuate very greatly
Definitely.
with respect to macroeconomic conditions, and so our process, if we're able to utilize bio-based feedstocks and inputs, we're able to, our techno-economic models project that we're able to have more stable costs over time than some of the traditionally derived propylene.
For sure. Yeah. And then there's the geopolitical angle of that kind of thing too.
Just
So,
utilizing fossil fuels.
yeah. Cool. Well, yeah. Well, thanks very much for the talk.
Of course, yeah, no problem.
Yeah, thank you so much, Kristian. Really appreciate your time. And yeah, hopefully this will be a good inspiration for sort of scaling up for the members of the challenge post-challenge. Don't, as Kristian said, don't maybe focus on that too much while you're getting your things ready, but we do want to help people make that leap to the next level. So thank you
Absolutely.
so much, Kristian, and thank you everyone for coming.